Good morning. Happy St. Patrick's Day. I'm wearing the only green thing that I have, and it's not even that green. I should probably do something about that. But anyways, fun day today. We get to see our second type of question. So remember, I'm going to be talking about all these question types, but the skills that we learned from the previous section with one sample proportion questions, we're going to apply those to the different types. So this is the first time where you're going to see that in action. Okay, and so it's kind of a fun time because we spent all that time laying out the groundwork for confidence intervals and hypothesis testing and checking the conditions and all that fun stuff. And so now we're going to apply it again, okay? I'm not going to do any review. We're just going to jump right into it. Okay, so today, we will introduce the second type of question that we will consider, introduce, and maybe I'll say a second type of question. And typically I call it a two sample proportion question. Proportion question. Okay. It's all in the name. And I know that's annoying to say because usually when you're first learning this stuff, it's kind of frustrating when your teacher says, oh, it's just in the name, just read it. And that doesn't come naturally until you've seen it a few times, okay, but it is all in the name. And so we're going to now have two samples. And we want to compare their proportions, right? So if we want to know, for example, how many, I'm trying to not think of any morbid examples, but usually things like what proportion of people who took drug A had a bad reaction versus the proportion of people who took drug B had a bad reaction, right? 16 out of 42 had a bad reaction, and maybe 21 out of 54 had a bad reaction, right? And so then we have these two samples that we can compare, and we want to compare the proportion. Whereas before, we had one sample proportion that we wanted to compare to some number, right? So things are going to change a little bit, but the ideas are all there and they're all the same. So we have two samples and we want to compare their proportions. Okay. So when you read the question, you're going to need to figure out, okay, do I have one sample? And do I have a proportion in there somewhere? Or do I have two samples, each with their own sample proportion? Okay. And then that's what you would want to compare. So consider, for example, in a study, and I'm just making this up off the top of my head, but just so you can see something where how it would present itself. Okay, so in a study, 16 out of, I don't know, 42 people had a bad reaction. I'm just kind of skirting around what it means to have a bad reaction, but let's just pretend. Okay, and so 16 out of 42 people had a bad reaction to drug. To drug A. while maybe 21 out of 54 people had a bad reaction, to drug B. Okay, something like that. And then we can ask questions like, is there a significant difference in the proportion of people who have bad reactions to drug A versus drug B? Right, so we could ask, so if it's a hypothesis testing question, it might follow up with, is there evidence of a difference in the proportions of bad reactions? I'm trying to have reasonable language skills here, but it's hard. So is there evidence of a difference in the proportions of bad reactions from drug A versus drug B? And you can adjust your alpha level, right, to be more or potentially less sure. In this case, if you're trying to establish that there's a difference, for example, if you own one of the drugs, then you want to be really confident in saying that you have found a difference, right, ideally. And so then you would lower your alpha level. Right. Whereas if it's a confidence interval, usually you would say build a some percent, a 95% confidence interval, right? But really what a confidence interval does is it tells you how large the difference is. Okay, so it would say build a 95% confidence interval for the difference in the proportions, of bad reactions from drug A and drug B. Bad reactions from drug A versus drug B. Okay, so a confidence interval is going to give us the plausible values for the difference. Plausible values for the difference. Okay. So let's think about this. So I clearly have a drug A sample and a drug B sample, and each of them have a proportion. So what I would do is I can denote these with p hats still, because they are sample proportions, but I would put a little subscript on to denote if it's from drug A or drug B. Okay. And so here, let's say we've been given, and remember, there are two different ways that we can give information in terms of proportions, right? Here I've given the number of successes out of n, right, our sample size for each of the drugs. I could have just given a percentage of the 42 people, and then you would have to find the number of successes. But you know how to do that, and that's the same as for one sample. Now we just have two that we have to deal with. So we're given that XA, remember X, we typically use it to denote the number of successes. And so the number of successes in group A, number of successes in A was 16, and the sample size of A was 42. And we were given XB, which was, I want to say 21. Oh, I should write this out. It's getting, oops, 54. There. Sloppy. And NB was 54. I just wrote it out. Okay. So in this case, we're given the number of successes and the sample sizes. And so now we have to check the conditions for each of these samples, right? So here we have a sample for drug A. And this is for drug B. So we have two samples and we have proportions from each of them. Okay. So notice here that in both of the cases, right, for the hypothesis testing, is there evidence of a difference in the proportions? And then build a confidence interval for the difference in the proportions, right? So how can I talk about the difference in the proportions, right? Notice how both of these are talking about the same parameter. Ugh, okay, that parameter is going to be, so the difference in the proportions is going to be the population proportion of A versus B. Now, it doesn't matter what order you do those in, as long as you're consistent. Okay, so here, the order of subtraction doesn't matter. As long as you are consistent. Okay. So the parameter we're trying to learn about is PA minus PB. Okay. And so this is the new thing that we're interested in, right? We're trying to do a hypothesis test to learn about how this difference behaves. And then we try to build a confidence interval to try to figure out where this value might be. Okay. And so the parameter here that we're now interested in, and I'm on a new page, so just put it right there. So the parameter is PA minus PB. But we only have sample information, right? Same as before. So what are we supposed to do, right? Well, we use a point estimate. What do you think a good point estimate would be? Well, probably P hat A or PA hat minus PB hat. Gets wordy, right? So the point estimate is PA hat minus PB hat. Make this look okay. Fair enough. Okay. So then if we think about how we calculate confidence intervals and hypothesis tests, right, the next thing that we need is the standard error of the point estimate. And this is where things get a little bit dicey. Okay. And so I'm going to parking lot that, but in general, and I'm going to steal it from these old notes that I didn't post, but I didn't post them on purpose because they're kind of outdated in a way. So I'm going to steal what I need here, and I guess I can post them, but I didn't want you to get confused by them. So they're all in a wrong order. So I'm going to grab what I want out of it. So here, as the sample size increases, the sampling distribution of, in general, we just use a P1 hat minus P2 hat, right? Here we're talking about drug A and B, but so you would want to match your subscripts to the sample information that you have, right? Maybe it's males, females, maybe it's cats and dogs. I don't know, doesn't matter, right? So you'd want to adjust your subscripts. So as the sample size is, right, because I've got 2 sample sizes, and they don't have to be the same, right? That's what we saw before, and that's fine. As the sample sizes increase, the sampling distribution of the difference becomes approximately normal. Okay, so for large enough, N1 and N2, and I'm going to show you how to check that. It's very similar to what we did before, right? The conditions that we checked for one sample proportion, we're essentially going to check them again, but for both samples, right? So now I have 2 samples, I have to check both of them. And there's a couple of tweaks, but in general, they're the same conditions. So then what we're looking at is the difference in the proportions is approximately normal. Okay, and it's centered on the difference, the population difference. That's fine. And then we have this huge standard error. Okay, and so it's P1 Q1 over N1 and P2 Q2 over N2. Okay. So here's the kind of the kicker, I guess. When doing a hypothesis test comparing 2 proportions, we're going to use the pooled proportion. Okay, so what we do is we take both samples and we throw them into one pot. So we have a total number of successes and a total sample size, and that is your pooled proportion. So this pooled proportion P hat is different from the one sample proportion P hat because now we have 2 samples. So you have to keep those straight. If you're in a 2 sample situation, then P hat is the pooled proportion. Okay. And so here I want to, when doing a hypothesis test, comparing 2 proportions, we're going to use the pooled proportion. Okay. And the formula is also on your kind of formula sheet. So you should probably put it on your own formula sheet or whatever kind of summary notes that you're building. So I'm going to grab that so we can have a look. And I know we haven't talked about any of this yet, but we have gone through the motions and we know what a hypothesis test is. We know what a null hypothesis is. I know what a test statistic is and what it does, right? And so I know what a confidence interval is. So now you can kind of look at this formula sheet excerpt, right? And so now we're looking at 2 sample proportions. And we can kind of pick our way through this. We haven't seen it explicitly yet, but if I want to do a hypothesis test for P1 minus P2, my null hypothesis is that they are the same, right? I have to assume that they're the same until I have proof otherwise, right? And then my test statistic here is a little bit involved. And of course, we're going to pick this thing apart, but this is how we calculate our Z-score. So it's still going to yield a Z-score. Once we have a Z-score, you know how to find the p-value. And once you have the p-value, you know how to state the conclusion and draw your conclusion, right? So that's all kind of on rails now. I know it's probably not feeling like it, but it will be. Okay, so once you have a Z, you're in the clear, right? So it's just going to be a matter of calculating this Z. And it even clarifies that where the P hat is this, where this P hat Q hat is the pooled proportion, which you could either just figure out the number of successes combined over the number of individuals combined, or if you prefer, if you only have the P hats, so P1 hat and P2 hats, then you could calculate the number of successes by multiplying them by their respective sample sizes, right? But that's a little bit more involved. Usually you just have the number of successes and the number of individuals and just kind of combine them. Whereas the confidence interval for P1 minus P2, of course, it's centered on the estimate of that difference, and plus minus Z star, you already know how to find the Z star, so this is the same as before. And then we take the square root of, and in this case, notice how this standard error is slightly different from here in the test statistic. We saw that exact same thing happening in the one sample proportion, right? And so we're used to seeing that, but luckily that's not always going to be the case. Often they're going to be the same standard error, so you don't have to keep track of that much longer. Always for proportions though. Okay, so a little bit tricky. So P1 hat, Q1 hat over N1, and P2 hat, Q2 hat over N2. Add those up, then take the square root. Usually people forget to take the square root, and that messes up your interval. Okay. And so depending on if we're going to do a confidence interval or a hypothesis test, how we find the standard error is going to be a little bit different. Okay. So for large N1 and N2, that leads us to our conditions, right? So we have to check our conditions. Oops. Before we can do a hypothesis test or build a confidence interval, before we can do a hypothesis test or build a confidence interval, we need to check the conditions or the assumptions. We need to check the conditions / state the assumptions, right? We saw that before where, okay, we're checking the conditions. If it's not said explicitly in the question that the sample was randomly selected, for example, I have to assume that it was randomly selected. So I have to say that that's what I'm assuming. Okay, so then we need to check the conditions / state the assumptions. Okay. And in the 2 sample proportion case, we have to check it for both samples. In the 2 sample proportion case, and maybe I'll change this to in a 2 sample proportion question, we need to check the conditions for both samples. We need to check the conditions for both samples. And if the question is asking us to build a confidence interval as well as a hypothesis test, then you have to check all of those conditions, right? So you've kind of got 4 different sets of things that you have to keep track of, right? Am I doing 1 sample, 2 samples, confidence interval and a hypothesis test, or just one of those? So there's lots to keep track of there. All right, so a lot of these conditions are the same, and I want to highlight the ones that are new. Okay, so the conditions. First, we're checking independence. Can I assume independence? Now, it's the same as the 1 sample, but we have to check it for both, right? So the first condition is randomly selected. Both samples must be randomly selected. Okay. The optional one, I'll put it as option 2. So this one's optional. It's more of a show-off thing, right? The other thing is the n less than 10%, but now, of course, that applies to both samples. So N1 has to be less than 10% of population 1. And N2 has to be less than 10% of population 2. It's not crazy, but it's or crazy important, but because it's very rarely going to happen that you've collected too much of the population, but it is something to keep in mind. So that's why I keep highlighting it. And then the third option is the new option, which I'll highlight after I've written it, is that, okay, so I have these 2 samples. So the additional condition is that both samples, so these samples are independent of each other. Okay, so the samples must be independent of each other. Okay, so this is our new one. That's fair enough, right? If I'm assuming that I have these 2 samples and I have to make sure that they're independent of each other, right? Because otherwise that would affect the difference in proportions, right? Then I have to state that, right? You could argue that those 2 samples are independent of each other. For example, right, you're not looking at twin data, right? Because then your observations would be dependent, right? Depending on what you're measuring, but most twin data is kind of out. What if you're looking at proportions of cats and dogs, right? Some measurement that you're interested in. Well, those are independent samples, right? Because there's no way that you can match one cat to one dog, and so you can assume that they're independent of each other. Okay. Okay, good. So I've got a page break here, so I'm actually going to start on the next page, even though it looks a little bit weird for now. But the normality condition is making sure that your sample sizes are large enough, right? And so here, I'll just clarify. Making sure sample sizes are large enough, right, to assume normality. Right? It's not until I get to say things for, you know, the 7th to 10th time that it's really going to start to sink in. So I want to highlight this again so it's not so murky here, or potentially. So as the sample size increases, okay, then the sampling distribution becomes approximately normal, okay, and that's what we want, because a z-score assumes that we have a normal distribution, right? So for large N1 and N2, and so that's the condition that we're checking now, is, okay, do I have a large enough N1 and N2 to assume normality? Okay. And so the normality condition depends on if you are doing a hypothesis test or a confidence interval. Okay. Because the hypothesis test is kind of the way different one from before, I want to start there. So depending on whether we are doing a hypothesis test or a confidence interval, we check different conditions, right? Or we check all of them if we're doing both. We check different conditions, or we check all of them if we are doing both a hypothesis test or and a confidence interval, I should say. So for a hypothesis test, do you remember the conditions for the hypothesis test? For the one sample, it relied on knowing the null hypothesis, right? P is equal to some P naught, some null value, right? We don't have that anymore because we're going to be comparing P1 to P2, right? And so we don't have a value to compare them to anymore. And so what we use is we are going to check the conditions using the pooled proportions. And so here, if you have a hypothesis test, it uses the pooled proportion. P hat, which is the number or the total number of successes over the total sample size. Or if you prefer, right, it's x1 plus x2 over n1 plus n2, right? Or n1 p1 hat plus n2 p2 hat, right? But usually I would have found my successes separately just so I don't bog down that calculation. And so even if you're given those sample proportions for each sample, right away you can calculate the number of successes, and then you can use this kind of, I think, easier formula than the everything in one. Okay. And so what we check for, if we're doing a hypothesis test, we're going to check, check that n1 p hat is greater than or equal to 10 and n1 q hat is greater than or equal to 10. And n2 also has to satisfy that criteria. N2 q2 hat, oh, sorry, q hat, clean that up. Right, so these here are the pooled proportions. And of course, Q hat is 1 minus P hat, right? And you have to check it for sample 1. And you have to check it for sample 2. This is all tedious, right? It's not hard. And especially because you're going to be working open book, you can have notes to refer to, but I think once you've done enough of them, it's going to start to flow. And I personally really like tedious things. I like knowing that I'm doing what I should be doing. And I know not everyone's the same way, but especially for something hard like this, once you kind of get the hang of it, then, you know, you just go ahead and plug in these numbers, and you're just trying to make sure that you have greater than or equal to 10, and it'll always check out, right? But you have to show that you checked it. Okay, and good. So that's what we check if we have to do a hypothesis test versus if we are doing a confidence interval. A confidence interval. Oh, and I guess I should clarify that really we're checking the expected number of successes and failures in each sample. Okay, so maybe before I go on to the confidence interval, so for the hypothesis test, we're checking that we have at least 10 expected successes and failures in each sample. That's the same as before, right? The expected number of successes and failures, but now the expectation is riding on the pooled proportion, right? So that's fine, because that is what you would expect in each sample. All right. So if you're doing a confidence interval, you get to just use your sample data. And so now, let's see what I wrote here. You're going to be checking that we have at least 10 observed successes and failures in each sample. So checking that we have at least 10 observed, at least 10 observed successes and failures in each sample. How did we do that? Well, we did it for the one sample proportion. That's when we had to take n times p hat. But now I have two samples, so I'm going to look at n1 times p1 hat, which is equal to x1, right? If you have x1, you can just use that. And that's the same for one sample proportion, but I wanted to really drill into that you can have the n1 p1 hat, depending on how your question is worded. Has to be greater than or equal to 10, and n1 q1 hat, which is n1 minus x1, has to be greater than or equal to 10. So now I'm just giving you some options, and I'm going to do second sample over here. N2, oops, I don't know why I went for q first. P2 hat has to, which is x2, has to be greater than or equal to 10, and n2 q2 hat, which is n2 minus x2, right? If you're not a success, then it's a failure. Oh, my laptop's doing something weird here. Let me just tell it to calm down. Okay. Right. Your sample size minus the number of successes gives you the number of failures, right? Which is greater than or equal to 10, right? So I have to check it for sample 1 and for sample 2. Okay, good. So let's see here. So we have to check the conditions, right? And then once we've checked the conditions, and they will always check out, then we're going to go ahead and we're going to actually do a hypothesis test or confidence interval. I want to start with I almost said confidence interval because it's easier, or I think it's easier, less steps. But I want to start with the hypothesis test and kind of iron out the details. And then I want to talk about the confidence interval. And then we're going to do an example. So it's a little bit discombobulated until we've seen an example. But there's also kind of things that I want to highlight and work through without an example, right? Just in general theory. Okay. So if we're doing, oops, I don't want that color, I want this color. So for a hypothesis test, for a difference in proportions, right? So that's a 2 sample proportions question, right, is going to analyze the difference in proportions. What's my my null hypothesis? We've already seen it, and maybe I'll kind of Step one is to state your hypotheses. So we have them on that formula sheet, okay? And of course, if we think back to hypothesis testing for one sample proportion, what did we start off assuming? We had to assume that the sample proportion, right, or the parameter that we're interested in is the same as the value we're comparing it to, right? We don't think that's true usually, but that's what we have to start off assuming. And so we do the same thing, right? If we're interested in, is there a difference in the proportions? The first thing you have to do is you have to assume that they are the same, right? Until you have proof otherwise. So I like to write my null hypothesis like this: P1 is equal to P2, right? A couple of things that we notice, right? Your null hypothesis, H naught always has an equal sign. Okay. And maybe I should write that out in words, equal sign. Okay. What are some other things we notice? P1 and P2, right? Those are the population proportions, right? So we always have to hypothesize about the parameter. We always hypothesize about the parameter. And then finally, overall, right? P1 is equal to P2. We assume the proportions are the same until we have found proof otherwise, right? Found proof against it. Until we have found proof against it. What does that mean in this case? If I've found proof against it, well, that means that they're not close together enough to be considered essentially the same, right? So that equal sign is not statistically significantly different. So they're allowed to be, similar, but once we take into account the spread, if we see that they're truly far apart from each other, then we wouldn't call them the same thing, right? And so that can get confusing because it incorporates the spread, right? How big of a difference am I expecting to see, right? And so, so that is the difference in the proportions statistically significantly different? Is the difference in proportions, and I'm going to go over the top here and say statistically significantly different, although usually we drop the statistically because the significance is all of statistics. And so you don't need to say that, but it emphasizes, right? Is the difference in proportion statistically significantly different? Different from what? Well, is P1 different from P2? Well, if they're basically the same, then the difference of them would be 0, right? Remember, we're talking about the difference. And so different from 0. So another way, I hilariously, an alternative way of writing the null hypothesis, I'm not going to say that, that's confusing. But another way that we could write the null hypothesis is P1 minus P2 equals 0. Right? So another way to write the hypotheses is H naught is that P1 minus P2 equals 0. Yeah. That's the same thing. If I subtract P2 from both sides here, I get 0 on the right-hand side and I get P1 minus P2 on the left-hand side, right? So they're the same. I just think that this is an easier way to look at the null hypothesis, right? Because I always have an equal sign and then I don't have to worry about P1 and P2. However, remember, initially we said, okay, my parameter that I'm interested in is P1 minus P2, right? And so that's technically what we're doing. And you can consider values other than 0, but the methods that we're outlining here only apply to when you're looking at 0. And it's very rare that you would want to show that the difference in proportions is equal to or different from 0.1 or something like that, right? If you want to show that there's a difference, not just beyond 0, but greater than 0.1, for example. It happens, but just as a quick little side note, we can consider values, consider differences other than 0, but it would require different techniques. But it would require different techniques, slightly different techniques. For example, the pooled proportion only works for if you're doing a difference of 0, right? And so you'd have to get around that, but it would require different techniques not covered in this course. Okay. So however you want to write your null hypothesis, you should match your alternative hypothesis to whatever you write your null hypothesis. Of course, we're working in an online format, and so then you should be able to recognize either of these and work with either of them, right? But maybe you have a personal preference, but it's okay. Okay. So what about our alternative hypothesis? If we want to know if there's a difference between P1 and P2, then that's easy enough. Then my alternative hypothesis is, so if I want to know if there's a difference, then my alternative hypothesis is that P1 is not equal to P2, right? Or P1 minus P2, is not equal to 0. That's like the easiest version. What if I want to know if P1 is less than P2? So that's why I prefer this this method of writing out my alternative hypothesis, because then I can just translate that into an inequality. So then my alternative is that P1 is less than P2. The equality is taken care of in the null hypothesis. And sometimes I'll mention this here. It's not something I'm gonna harp on too much. But if you have less than here, then the null hypothesis is really greater than or equal to, but I just stick with equal to. Okay. And the alternative hypothesis for the one-sided test, which is what this is, gets a little bit weird, right? If I'm thinking about P1 minus P2, if P1 is less than P2, then I have a smaller number, so I pick a number 2 and I subtract a larger number 4, I get a negative number that's less than 0. right? So you'd have to do a little bit of legwork here, but P1 minus P2 is less than 0. All right? Or P1 greater than P2. And of course, it depends on the question, right? So if you're testing a difference, then that's the easiest option, right? But if you want to prove that P2 is significantly less than P1, okay, that's this scenario, right? So you'd have to really keep track of what the question is asking you for. So the alternative hypothesis in terms of just P1 and P2, P1 is greater than P2, or P1 minus P2. So now we've looked at all the options, so we know it's going to be greater than, but let's just consider this, right? So if P1 is greater than P2, so now I have 4 minus 2, just picking random, just any numbers that work, right? 4 is greater than 2. And so 4 minus 2 gives me 2, which is a positive number. So that's going to be greater than 0. Okay. Again, these are called one-sided tests, one-sided or one-tailed tests. And this is a two-sided test or two-tailed, but I usually just say two-sided. Okay, that's going to come into play again for our p-values, right? We need to keep track of this for finding our p-value later. Yeah. Okay. So one-sided test, two-sided test, we kind of parking lot that and make a note somewhere, and then we come back to it later in step 3. Okay. So now we're ready for step 2. So we've set up our null and alternative hypotheses, and we have a couple of different options, but just pick one that you like and then go with that. Step 2 is do the test. And let's see if it's still the last thing I copied. It is. And I'm gonna just put that there. Okay. Doing the test is this part of the formula sheet, right? And remember, we said that the pooled proportion comes into play. So you've set up your null and alternative hypotheses, and if you're ever unsure, then the default is not equal to in your alternative hypothesis. You're going to run a two-sided test if you're ever unsure. Okay. And so because it guards against both, right? You don't want to be swayed one way or another if you're not sure which way it should be going. But anyways, so the default is not equal to. Okay, so in order to do the test, which is calculating the Z-score, which is a test statistic, okay, I need the pooled proportion. Okay, so the first thing I'm going to do is calculate the pooled proportion. So we need the pooled proportion. And P hat is, oops, is the number of, or the total successes. And maybe what I'll do, because it's written on that formula sheet excerpt that I put in there, what I'm going to do is just do x1 plus x2 over n1 plus n2. Because I have all those values, so I may as well just plug them in. Right? Not too bad. Okay. Oh, I forgot. We are not working with the numbers yet. I forgot that I had abandoned the drug example because I had made it up, so I don't know what's going to happen of it. We can work through it, but I've got a better kind of more prescribed example in mind. Okay, so we need the pooled proportion. So that's either going to be x1 plus x2 over n1 plus n2, or depending on the information that you have, p hat is n1 x, p1 hat plus n2 p2 hat over n1 plus n2. And that's actually on here, right? So you don't have to keep track of that. Okay, so you need the pooled proportion. And then our z-score is going to be z, which is a test statistic. And that's why I call this do the test, which really says calculate the test statistic. Feel like you're ready to hear some of this terminology, right? And so in the end, we're going to call this a z-test, right? It's a hypothesis test that uses a z-score as the test statistic. Hard to say. Okay, so z is p1 hat minus p2 hat. And there's something I want to add there, but I'm going to leave that for now, over the square root of p hat q hat times, it's been a while, so 1 over n1 plus 1 over n2. I need to look at the formula there. Now I'll have it memorized. Okay, so technically what's going on here is we want to see how far is my sample difference from my hypothesized difference. Okay, and so really this is my sample difference. And I want to see how far is it from my hypothesized difference. But my hypothesized difference, and what color can I use? Let's maybe use pink. Minus P1 minus P2, which is the hypothesized difference. Equals 0. Right, my null hypothesis is that P1 is equal to P2, meaning the difference is 0. Or if you want to explicitly say it, P1 minus P2 is equal to 0. That's your null hypothesis, right? So this value is going to be 0 regardless. So again, if you're testing something other than 0, you'd have to look up different techniques. You have the tools to handle it, but we're not going to cover it in this course. So we're going to focus only on a difference of 0, which is the majority of cases. Okay? I'm not going to set you up with something that we don't really use. So of course, 0 is the most common. Okay, and so that's why, so this all goes to 0, right? So this is all equal to 0 or minus 0. This is minus 0. So it's not even included on the formula sheet. So we exclude it on the formula sheet. Okay. Because minus 0, it doesn't matter, right? But technically what you're doing is you're taking, okay, I saw this difference. I saw a difference of 0.2. How different is 0.2 from 0 if I take into account the spread? So I like to think of it as a difference of 0.2 centimeters maybe in the length of a dog, right? And so you've got these two dogs, and I'm kind of mix and matching examples here, but it really emphasizes the role that the spread plays, right? So if I have a 0.2 centimeter difference in the length of two dogs, that's not weird. I would expect that, right? Because the difference in the lengths of dogs is huge, right? So I've got a big spread. If I look at mosquitoes or ants or something with not very much spread at all, then a difference of 0.2 might be huge, right? So we have to consider the spread, right? And so the spread is using that pooled proportion. Okay. And so here, what color haven't I used? Maybe this one. So where this p hat comes from up here, right? And then of course, q hat is 1 minus p hat. I don't think I should have to say that anymore, but I know it can be confusing in the beginning. Oops. Different color wheel. Okay. Once you have a z-score, right, then finding your p-value is the same as before. You can use the z-table, or you can use the z-distribution in R or Excel to find the p-values, right? So step 3, find the p-value. Once you have calculated z in step 2, the z itself behaves the same as all other z's, right? So once we've calculated a z in step 2, we can use the z-table or R or Excel if you like, Python, anything really. An online calculator probably gives you the probability of z. So once we've calculated a z in step 2, we can use the z-table just as we did in, the z-table to find the one-sided or two-sided p-value. Two-sided p-value, we just find the area in one tail, multiply it by 2 to kind of pretend that it happened in the other tail, right? To find the one-sided or the two-sided p-value, let me read this. Once we have calculated a z in step 2, we can use the z-table to find the one-sided or the two-sided p-value in the same way that we did in one sample proportion. In the same way we did with one sample proportion. Right? So once you've reduced it to a z, you know how z works, then you're just off to the races, right? So now, even if you look up how to do a difference of proportion other than 0, then I don't know what the test statistic is, but if it is a z-score, you know how to do that, right? So you just need to make some changes in your calculation probably, and then you can go from there. So then, so really what happened is step 3 has not changed from before, from the one sample proportion question. Right. What we'll also, so maybe notice here, step 3 is not changed, and neither will step 4, except for what your conclusion is about, right? Now your conclusion is about the difference in the proportions, right? But that's going to come from the question. So that's the same as before. So notice that step 3 is not changed from the one sample proportion question. And we will also, and step 4 also remains unchanged. Except the conclusion, the final conclusion, except the final conclusion will be about the difference in proportions. Will be about the difference in proportions. Just to recap, right? What is our step 4? Right? It's going to be the same as before, but it doesn't hurt to re-emphasize. So step 4, oops, is your conclusion. First part of your conclusion is comparing your p-value to your alpha level. Right? That's the same as before. There's no changes here. Right, so part 1 is compare the p-value to the alpha level. Right, and the default alpha level, let's just say alpha. The default alpha level is 0.05. Right. So compare the p-value to the alpha level, depending on if it's less than or greater than the alpha level. Right? If the p-value is small enough, right, then you have enough evidence to reject H0, right? So if the p-value is less than the alpha level, then you have enough evidence to reject H0. So step 2 is your conclusion in terms of H0. Which has kind of, if the p-value is less than the alpha level, we have enough evidence to reject H0 in favor of HA, but I'll leave it at that. Or if the p-value is, I want to say not less than the alpha level. And so if the p-value is greater than the alpha level, I'll say greater than or equal to, kind of flexible here. Depends on how expensive it is to make a type 1 or a type 2 error. Type 1 error, sorry. But that's kind of beyond the scope of this course. So if the p-value is greater than or equal to, let's stick to that. The alpha level, we do not have enough evidence to reject H0. So we do not have enough evidence to reject H0. And then finally, your conclusion in terms of the question, which is going to be about the difference in proportions. Your conclusion in terms of the question which will be about the difference in proportions. And I should maybe clarify here, population proportions. Okay. We've got quite a little bit of time left. I want to maybe start an example so we can kind of pull it all together. And I don't know, with a little bit of luck, we might even finish it. Oh, no, I know. Confidence intervals. We have to talk about confidence intervals. There we go. Because my plan was to have you watch the example and work through the example tomorrow for the video tomorrow. So it's all coming together now. What if I want to do a confidence interval? Well, it's kind of easy enough. Once we have the conditions checked, getting stuck on my words here. Once we have checked the conditions and we have the formula, which I've already given to you in that formula sheet, right? And so I'll paste that in here again, and I'm going to crop it down so that it's just the stuff that we need. Okay. And the confidence interval is a confidence interval for the difference in population proportions, for the difference in population proportions. Which is P1 minus P2. Okay, so it's a confidence interval, and just like the hypothesis test, we're not talking about the sample, we're using the sample to learn about what the population might look like, right? And so same thing with the confidence interval, we build this interval to try to figure out what P1 minus P2 might be, right? We rely on P1 hat minus P2 hat because that's our best guess, but then we build this buffer around it. So just like before, we have this margin of error, we have the standard error, and we have a critical value. So kind of working out backwards, Z star is the critical value and you find it the same way as we did before, right? The critical value is the same as before. That's always nice, right? Then we have the standard error. This is the standard error of P1 hat minus P2 hat. Right, it's always the standard error for whatever the statistic is, or the point estimate. And so in this case, the standard error for those two in the confidence interval case is the square root of P1 Q1 hat, or P1 hat Q1 hat over N1. Very tedious to read out, but plus P2 hat Q2 hat over N2. Okay, so order of operations is going to be really important here. I usually find one, put it to the side, so I store it in my calculator, so I keep all my decimal places, and then I calculate the other one, and then I add them together, and then I take the square root, and then I multiply by the critical value, right? And then, so this is still called, overall, this is your margin of error. So the terminology stays the same, but how we calculate them are just slightly different. Okay. So when you interpret your confidence interval, right, we're going to still get a lower and an upper bound, right? And so your confidence interval is still going to look like this, right? So I've got some lower value, comma, some upper value, and interval notation uses rounded brackets, right? Because we don't go to those values. But just use rounded brackets, that's fine. So you find your confidence interval, right? You get some lower value and some upper value, and then your interpretation is the same as before. We are some percent confident. Oops. Confident, the interval from blank to blank. And it's really important that you start with your lower bound to your upper bound. Captures the difference in population proportions, right? Because you're always talking about, it's a confidence interval for P1 minus P2. So you're always talking about the parameter, right? Captures, and then here from the question, right, you would steal this and say the difference in population proportions. So whatever that translates to, captures the true difference. So sometimes I like to emphasize that it's the population proportion by saying true, right? So the true difference in proportions of bad effects or bad reactions to drug A versus drug B, something like that. Okay. Notice that the slower and upper value, those are differences, right? And so, so just a quick side note that these guys, remember that these are differences. So if 0 is in the interval, what does that mean? Then it's possible or plausible that a difference of 0 can happen, right? Which is the same as you would not be able to reject the null hypothesis, right? So I am going to give you this question because what I want you to do is I want you to read through and work through this question before you watch the video that I'll post later today, but it's for tomorrow. Okay, so for video tomorrow, work through this question. I think I fixed the typos, but maybe not. Maybe I forgot some. Okay. So it's an example, and I also want to sneak in here, and I hope that I did it here. Check that the conditions for inference are satisfied. Okay. So what we did today was we laid out the groundwork, all the theory that you need. So you have all the tools. It's just hard to apply it to a question, right? But you need to work at it. And so work through this problem. And then if you find that it matches the notes that I post, then that's awesome. And if not, you can watch the video and just kind of fill in the gaps tomorrow. But if it all makes sense and it's all good, then you don't have to watch the video tomorrow. All right. If it all makes sense. All right. So that's good. I know I'm out of time. If you have any questions, let me know. Otherwise, happy St. Patrick's Day, and also have a great weekend, and I'll see you next week. Stop this here.